Hi everyone, welcome to my channel. In today's video, we are going to discuss the topic work, energy, power. Okay. Again, this video is going to be a quick recap of the chapter for your entrance preparation, that is JEE or NEET. Okay. So now to start with, first of all, we need to understand the term work. Okay. Now you may think that, okay, I know the definition of work. What is so great about that with regard to entrance preparation? Okay. Now for entrance preparation, see, core concepts, fundamentals, these need to be very strong. Okay. Now when I say work, then it implies, like suppose this is a horizontal surface and suppose this is a block of mass m and it is acted upon by some force F, and suppose this is the displacement. Okay, theta is the angle between force and displacement. Now work is said to be done by this force F, provided under the action of this force there should be some displacement of this body. So suppose this block moves from this position to this position. Okay, now this is the displacement S. Okay, this is the displacement S. So when the force acts on the body, there must be some displacement on the body. Okay, so that is one condition for work done by this force. Achha. Now I can resolve this force into two components. This is theta, so this will be F cos theta and this will be F sin theta. Okay. So F cos theta is the component of force in the direction of displacement. So for work to be done, there must be a component of force along the direction of displacement. Okay, there must be a component of force along the direction of displacement, and it is this component of force which is doing work. No work is done by this component, F sin theta component, which is perpendicular to the displacement. Okay, so I can call this as F perpendicular and this F cos theta as F parallel. Okay, so this work is done by this component of force which is parallel to displacement. No work is done by this component. No work is done. Okay, so force, when a force acts on a body and because of that force there is a displacement, work is said to be done provided because of this action of force there is a displacement in the body and there must be a component of force in the direction of displacement. Okay, now see, once this question was asked, like suppose this is a block MA and this is another block MB. MA is the mass of this block, MB is the mass of this block. They are placed on a horizontal smooth surface and this is force F, and suppose these two blocks, they move together. This force acts on this block. This capital F force, it is acting on this block. This block, it is contact with this block. And suppose they move through a distance S. Okay, they move through a distance S. Now, the question was, what is the work done by this force on mass MB? What is the work done by this force on mass MB? So, in this case, work done, it will be how much? It will be 0. Why? Because this force is acting on this block of mass MA. It is not acting on this block. So, see, this is the condition for this work done. Force acting on the body displaces it through some distance, so that the component of, there is a component of force along the direction of displacement. So, this force is acting on this body and it is causing the displacement. This force is acting on this body. Displacement on this block is produced by the contact force which is acting because of the contact of MA and MB, and that contact force is not this force. So work done by this force is 0. Okay, so this is one very important concept. Okay, now see, we have seen, like suppose this is a block of mass M and this is force, this is displacement, this angle is theta. Now we got work done is equal to F dot S, or we wrote it as W equal to Fs cos theta. Okay, so that implies, see, work done it can take positive value for theta value between 0 degree and 90 degree. Okay, it can be 0, work done can be 0 if theta is 0. Okay, and work done can also be negative if theta is greater than 90 degree. Suppose in this case, if there is friction, so frictional force, if the displacement is taking place in this direction, so for this block, on the lower surface of this block, frictional force will act in this direction. So if it is asked like work done by frictional force, so in that case it will be F S cos 180 degree. Force is in this direction, displacement is in this direction. Both are in opposite directions, so angle is 180 degree. Okay, this theta is the angle between force and displacement. So here force is, frictional force is this force. So cos 180 is minus 1. So Wf is equal to work done by frictional force, it is equal to minus Fs. So in this case, work done by frictional force is negative. Okay, so work done, if we calculate work done, the sign can be positive, can be negative, or can be 0 also. Okay. Now, let us see how to calculate the work done for a variable force. Okay, work done by variable force. Okay, now suppose this is force and this is displacement. Okay, and so force is varying like this with displacement. Then how to calculate the work done? You take one small interval, such a small interval. See here what force is changing continuously. So if I take a very small interval, so that for that small displacement dx, the force F is a constant. So for this part, if I calculate the area, it will be dW, which is equal to F dx. dW equal to F dx. So if you want to calculate, suppose this is initial position xi and this is final position xf. So if you want to calculate the work done between displacement from xi to xf, that means you have to calculate this total area. So that is dW. So work done from this point to this point, dW xi to xf, it is equal to xi to xf f dx. Okay, so this is work done is equal to integral x initial x final f dx. So this is how you can calculate the work done by a variable force. Okay, now let us see one example. Like what kind of force? I am talking about variable force. What kind of force is this variable force? So suppose you have a horizontal surface. This is a vertical wall, fixed vertical wall, and this is a spring, and a person is pulling this spring. Okay, he's holding the spring and he's pulling the spring in this direction. So there's a elongation x. Okay. Now see here, as you pull the spring, initially you don't have to apply much force, but as this elongation increases, this force also increases, because the spring force also increases. See, when you are pulling the spring, this is a spring force, and you are applying external force in this direction. So this spring force increases as this extension or elongation increases. Okay, so here this force which you are exerting on the spring is a variable force. Okay, we know that this spring force, it is equal to minus kx, isn't it? So that means the external force, it is equal to kx. Okay, so work done, suppose extension is from x initial to x final, kx dx. So if you integrate this, what do you get? W is equal to half kxf square minus half kxi square. Okay, so if the elongation of the spring is changed from xi to xf, this will be the work done. Okay. Now if initial elongation was 0 and final elongation is x, so in that case W will be equal to half kx squared. Now let us see one graph based question. Like suppose force is equal to 3x plus 5 Newton. Okay, this is the force, and this force acts on a body and displaces it from x equal to 2 meter to x equal to 4 meter. Okay, so this force, see again, this force is a variable force, and this force displaces a body from x equal to 2 meter to x equal to 4 meter. Okay, and suppose we have to find the work done. Okay, now we will approach this question in two ways. Okay, one is like, suppose if you draw a graph, this is f, this is x displacement. So 3x plus 5, so that means this will be a straight line. Okay, so this is the origin, so this will be 0, 5. Correct? Achha. Now x equal to 2 meter to x equal to 4 meter. So if I take this as x equal to 2, so this coordinate it becomes 2 comma 2 3 is 6 plus 5 11. So 2 comma 11. Correct? Similarly, if this is x is equal to 4 meter, so this is 4 3s are 12, 12 plus 5 17. So this is 4 comma 17, this coordinate. So if you are asked to calculate the work done, so that means you need to calculate the area under force displacement graph, this area, because for this particular interval you need to calculate the work done. You are asked, actually, no, you don't need, you are asked to calculate the work done for this interval. So what is the area of this? This is a trapezium, so this is half into length of this side is how much? This is 11, this is 17 plus 17, distance between the two parallel sides, so this is 2. Okay, so this is 2 gets cancelled, so this is 28 joule. So this is the work done. Okay, this is one way of approaching this question. And another way is this calculus. So W is equal to integral x equal to 2 meter to x equal to 4 meter f dx, so that is 3x plus 5 dx. So this is W is equal to 3x squared by 2 plus 5x. Limit is from x equal to 2 to x equal to 4. Okay, so this is W is equal to 4 square by 2 plus 5 4s are 20 minus 3 by 2 into 2 square minus 10. Okay, so this is 16 3 48 divided by 2 24 24 plus 20 minus this is 6 minus 10. So this is 44 minus 16. How much is 44 minus 16? 44 minus 16 is equal to 28 joule. Correct? So both ways you are getting the same result. Okay, so I hope this concept is clear to you. Okay, so now let's proceed. Now next is work energy theorem. Work energy theorem. Okay, now your NCERT textbook says that this work done, it is equal to change in kinetic energy. Change in kinetic energy. So that is work done, it is equal to half mv square minus half mu square, where u is the initial velocity, v is the final velocity. So this final kinetic energy minus initial kinetic energy. Okay, so this is work done. Okay, now from this we can conclude, like, if work done is positive, that is W is greater than 0. So it means kinetic energy of the body is increasing, because if this quantity is positive, that means final kinetic energy is greater than initial kinetic energy. Okay, so whenever positive work is done, kinetic energy of the system increases. Okay, now similarly, if work done is negative, it means kinetic energy of the system decreases. That is, in case of friction, work done by frictional force is negative. So when a body moves under the influence of frictional force, its kinetic energy decreases. Okay. So see, this is a basic idea, like this is what is given in your NCERT textbook. But according to work energy theorem, this total energy of the system remains constant. Okay. Total energy of a system remains constant. Like, it is not necessary always that work done is equal to change in kinetic energy. Now, work done can be equal to change in potential energy also. Okay. So the main concept is total energy of a isolated system is a conserved quantity. Okay. And like for example, suppose you have a track like this. This is a track, and suppose this is some sort of cart. Okay. These are the wheels, and it is coming like this, it reaches this point. This height is h. This height is h. Okay. Initially it is at rest. So here, initial energy is in the form of potential energy because of its height. So that is equal to mgh if m is the mass. Okay. It is at rest. So this is the initial energy ui, and ki is 0 because it is at rest. Okay. Now, when it is left, then it will come down. And why it is coming down? Because of gravitational force. Okay. And gravitational force is a conservative force. Gravitational force, it is a conservative force. Okay. It is a conservative force. Now, work done by conservative force is path independent. It only depends on final position and initial position. So that means in this case, total energy is going to be conserved. So total energy conserved means here also total energy will be, see, initial, what is total energy? If I add these two, so total energy E is equal to ui, initial total energy is equal to ui plus ki is equal to mgh. Okay. Now when it reaches this point, this is the zero height level, ground level. So here potential energy is equal to 0, and kinetic energy is half mv square. So that means final energy, E final, it is equal to half mv square. But so this is the total initial energy, this is the total final energy. Now if I use principle of conservation of energy, now why if I am saying that if I use, like why I am able to use it? I am able to use it because I know that total energy is conserved. Why I know that total energy is conserved? Because this motion is taking place under the influence of gravitational force, which is a conservative force. So total energy is conserved. So I can equate these two quantities. So I have half mv square is equal to mgh, or v is equal to square root of 2gh. Okay. So this will be the velocity at this particular location. Okay. So another interesting question, like suppose this is an inclined plane of inclination, theta is equal to 30 degree. Okay. And this is a block of mass m, where m is equal to 50 gram. Okay, m is equal to 50 gram. And it is at rest, and this is a horizontal plane. This is a horizontal plane. Okay. So this block starts with 0 initial velocity. So initial velocity is 0. It starts with 0 initial velocity. It comes down the inclined plane, and then it moves along the horizontal surface. Now see, this inclined plane and horizontal surface both are rough. So there is a friction. Coefficient of friction is 0.15. And because of this friction, it slides down and then moves on the horizontal surface and finally stops here. Okay. So final velocity is also 0. Okay. Now suppose this distance is s is equal to 50 centimeter. This part I don't know, that information is not given. Okay. Suppose this is some L. Now this part has friction, this part also has friction, and we are asked to calculate the work done by the frictional force. Total work done by frictional force in this part and in the horizontal part. Okay. Now if you want, you can pause the video and you can try on your own. okay, and then you can verify with my solution. Okay. Now see, for this part, if you see, the object is starting with zero initial velocity, so kinetic energy is 0. Okay, then see, this is mg, this is theta, so this is mg cos theta, this is mg sin theta. So it is mg sin theta is acting down the plane, but theta is 30 degree, it is given. This is the normal reaction, and this is the direction of the frictional force. So I have marked all the forces. So this mg sin theta is acting in this direction. So work done by this mg sin theta force, it will be positive because force is acting in this direction. Displacement is also in this direction. How much is the displacement from this point to this point? L. I don't know this L, but I need to find this value. Okay. So work done by this force mg sin theta will be positive work done mg sin theta multiplied by L. Okay. So this is positive work done. Now, how about this frictional force? Frictional force is also acting from this point to this point. Okay, it is also acting in this point. For this part, I am calculating the work done separately. Okay, so here, what is the friction? Friction is how much? Mu times normal reaction. Normal reaction is this quantity. So this is negative work done. Friction work done by friction is negative because frictional force is acting in this direction. Displacement is in this direction. So minus mu mg cos theta into L. So that is the work done by frictional force in this part. Work done by frictional force in this part, it is minus, again it will be negative, minus mu mg into S. This is equal to the final kinetic energy. Final kinetic energy stops, so final kinetic energy is also 0. Okay, so this I have written using principle of conservation of energy. Okay, now here see, m is known, theta is known, S is also known. Okay, so the only unknown quantity here, it is L. Okay, now if you simplify this equation, you get the value of L as 0.2 meter. 0.2 meter. Okay, so from this I can calculate the work done. See, I was asked to calculate the work done, total work done by friction. Now friction is acting at two parts. One is this inclined part and one is the horizontal part. So for the inclined part of length L, work done by friction force for this length L, it will be how much? It will be this quantity mu mg cos theta into L. Correct? And for this horizontal part, work done by friction for this displacement S, it will be mu mg into S. Okay, all these quantities are known. You can simplify it and you can verify it that the total work done, if you add these two, you get the total work done, and this will come out to be around 0.05 joule. Okay, you should try this and you will get it as 0.05 joule. Okay, so this is the concept to solve this question. Okay, the next term that we need to know is power. Okay, now power is basically rate of doing work. Rate of doing work means, what is the importance of power is, see, doing work is important, but all the more it is important like how fast you are doing work. Okay, so that is given by power, rate of doing work. Now see, whenever we talk about rate, we need to understand that there are two kind of rate, like delta and D. Okay, delta and D. This you might have learned when you learned the basics of calculus in class 11. See, when I write delta W by delta T, delta W by delta T. So that means I am talking about average power or mean power. Okay, but if I am writing dW by dt, so that means I am talking about instantaneous power. Instantaneous power, that is power at a particular instant of time. This is mean power, means power for a given interval of time. Okay, so that is the difference between average power or mean power and instantaneous power. Okay, now we will solve one question based on this term average power and instantaneous power. Okay, so this question is based on projectile motion. Like suppose this projectile is projected with velocity u at an angle theta, and this is the trajectory of the projectile. Okay, now suppose the projectile has mass m. Okay, so a body of mass m is thrown at an angle theta to the horizontal with initial velocity u. Find the mean power developed by the gravity. Mean power developed by the gravity over the whole time. Okay, over the whole time of motion. Okay, and instantaneous power of gravity as a function of time. Mean power, P mean, this you have to calculate for the whole time of motion, and instantaneous power at some time t, at arbitrary time t, it is asked. Okay, now if you see this mean power for total journey, for total time of motion, so time of motion means from this point to this point. Okay, this P mean power here, it is delta W by delta T. Delta T means total time of flight, and delta W means total work done, but work done is equal to change in kinetic energy. Delta kinetic energy. Okay, see, when a projectile is projected, suppose this velocity is u, here it comes down with same velocity u. So that means if initial kinetic energy is half mv square, final kinetic energy will also be half mv square. So that means this total kinetic energy, change in kinetic energy will be how much? 0. So that means mean power for the total journey, it will be equal to 0. Okay, for projectile motion, the mean power for total journey, it will be equal to 0. Next, we need to calculate instantaneous power at time t. That means at some arbitrary time t. Okay, so for that, see, that is also very easy. See, for that you need to understand that, see, P instantaneous, it is dw by dt. So d by dt, what is w? W is F dot s. So if a constant force is acting, so this will be F ds dot ds by dt. ds by dt is velocity. So instantaneous power, it is equal to F dot v. So instantaneous power, it is a dot product of force and velocity. Okay, so this on this concept we will solve this question of calculation of instantaneous power. Okay, so this is see, this is the initial velocity, this angle is theta. So suppose at this particular point we are going to calculate the power. It is asked like you need to calculate the power at some arbitrary time t. So at this instant, this is the trajectory. So at trajectory at any point, if you draw a tangent, the tangent will give you the direction of velocity. Okay. So if this is u, this is theta, so this will be u cos theta, and this will be u sin theta. Okay. So if this is v, it will have a horizontal component vx, vertical component vy. Okay. What is vx? Vx will be equal to u cos theta, because horizontal component of velocity do not change. So it is u cos theta. Okay. And what is vy? It will be u sin theta minus gt. Okay. So I can write this velocity v in vector form as u cos theta I cap plus u sin theta minus gt j cap. Okay. And see, when the projectile moves at each and every point, what is the direction of the gravity? You are asked to calculate the instantaneous power due to gravity. So gravitational force, it is acting in the downward direction. So force is mg. It is acting in the downward direction. Okay. So I can write this force as mg minus j cap. Why minus j cap? Because it is acting in the downward direction. Okay. So now instantaneous power, it is a dot product of force and velocity. This force is given, velocity is given. So what is P instantaneous? Dot product of these two quantities. So that is mg. This becomes gt minus u sin theta. So this is the expression for the instantaneous power. Okay. So I hope this concept is clear to you. Okay. So now let's proceed. So another interesting and important question also. A vehicle of mass m accelerates starting from rest while the engine supplies a constant power P. Okay, so power is P supplied by the engine, and we have to find the velocity as a function of time, and we need to find the expression for velocity as a function of time, and we also need to find the position of vehicle as a function of time. Okay, and what is given? Power, constant power is supplied by the engine. This information is given. Okay, so first is, see, from power we are asked to find the expression for velocity. Okay, so see, power, it is equal to force into velocity. Now what is this force? Force is mass into acceleration. Acceleration is dv by dt into velocity. So this is power. Okay, so v dv is equal to p by m dt. Okay, so if I integrate this, so this is 0 to t, this is 0 to v, so this is v square by 2, it is equal to pt by m. You are asked to find velocity as a function of time. So this is what? V is equal to 2 pt by m square root of this. So this is velocity as a function of time. Okay. Now then you are asked to express position as a function of time. Okay. Now this is velocity. So from velocity it is very easy to get position, because ds by dt, it is equal to 2p by m square root of this p power half. I can write this as like this. Okay, so this ds by dt, so if I take this dt over here, okay, then simply integrate this. So this is 0 to s, this is 0 to t, so this becomes s is equal to 2p by m square root of this, so t power half, so that is t power half plus 1 divided by half plus 1. Okay, so half plus 1 means this is 3 by 2, this becomes 2 by 3. Okay, so this I can write it as s is equal to 2 to the 4, 4 to the 8, 8 by 9 p by m square root of this p power 3 by 2. Okay, so this is the expression for displacement. Okay, next let us see about conservative and non-conservative forces. Non-conservative forces. See, basically, like conservative force means work done by conservative force is path independent. Okay. So gravitational force is a conservative force, electrostatic force is a conservative force. Non-conservative force means work done is path dependent. Like frictional force, it is a non-conservative force. Now when I say the force is conservative, that means we can write force as negative gradient of potential energy. For conservative force only we can define potential energy, and that relation between potential energy is and force, conservative force is negative gradient of potential energy. Okay, now from this I can define concept of equilibrium. Like we know that for equilibrium force is 0. Okay, force 0 implies du by dr, it is equal to 0. Okay, du by dr equal to 0. Now du by dr equal to 0 implies many things. Okay, like potential energy can be 0, potential energy can be maximum also. Okay, so we will see that from a graph. So suppose you have a graph of potential energy versus position. You have a graph like this. This is the graph. Okay, so as you can see for this part, if you calculate the slope at this part, so du by dr it will be equal to 0. For this part also du by dr equal to 0. For this part also du by dr it is equal to 0. Correct? Now here potential energy is minimum. Potential energy is minimum. Okay, U is minimum. Here potential energy is maximum. Potential energy is maximum. So when potential energy is maximum, see here force is 0, here force is 0, here also force is 0. So that means these three positions are equilibrium positions. But when potential energy is minimum, we will say that it is stable equilibrium. Say that this position corresponds to stable equilibrium. Stable equilibrium. Okay. Later on in the chapter simple harmonic motion, we will see that this oscillation takes place about position of stable equilibrium. Okay, like pendulum oscillating like this, spring mass system oscillating. So for all these cases, the oscillation takes place about stable equilibrium position. When potential energy is maximum, again force is 0. See here force is 0, here force is 0, here also force is 0. So that means all the 3 points, all the 3 locations belongs to equilibrium condition. Okay, but here it is stable equilibrium, here potential energy is maximum, here it is unstable equilibrium. Unstable equilibrium. And this part, horizontal part, flat part, this is called neutral equilibrium. Neutral equilibrium. It implies, like if a body is at this particular position, at position of lowest potential energy, and if it is slightly disturbed, then again it tries to come to that position of minimum potential energy. Okay, so that is called stable equilibrium. Now here if I place the same body at this particular location, it will remain at rest. It is in equilibrium. But if it is slightly disturbed, it will go in this direction. If it is slightly disturbed, it will go in this direction. It will not return to its original position. So that is why it is called unstable equilibrium. And neutral equilibrium implies, like body is at this particular position, it will remain at rest. If I push it, it will move to this position and again it will remain at rest. If I push it from this position to this position, here also it will remain at rest. So that is called neutral equilibrium. Okay. So this is the concept of 3 types of equilibrium. Okay. From this graph. Okay. I hope this graph is clear to you. Now for conservative force, we have seen that F is equal to minus du by dr. Okay. So from this I can write du is equal to minus F dot dr. Okay. Like see here why dot appears, because this is potential energy, this is force, this is displacement. Now when you are multiplying force and displacement, this multiplication is not going to be simple multiplication. Why not simple multiplication? Because they are vector quantities, and vector quantities when you multiply, now you can multiply like cross product or dot product, but potential energy is a scalar quantity, so this has to be a dot product. Okay, so this is potential energy. Now what is this? This is work done. So this is suppose initial potential energy, this is final potential energy. If you integrate this, so this is suppose initial position, final position. Okay, so this will be the work done. So this is minus W, this is U final minus U initial. So if I take minus sign over here, so work done is equal to U initial minus U final. Okay, but who is doing this work? This work is done by conservative force. Work done by conservative force. So for work done by conservative force, work done is equal to initial potential energy minus final potential energy. Okay. So what are the different types of conservative force? One is gravitational force. Gravitational force, it is a conservative force. Another type of conservative force is the spring force. Okay, spring force is also a conservative force. Okay, in class 12 we will study about electrostatics in Coulomb's law. So that is again we have already studied that. So that is also a type of conservative force. Now suppose this is the ground level, and suppose this is a block of mass m. It is lifted from ground level through height h. Okay. At particular instant, it is at this particular position. I am taking this block from ground level to height h. Okay. So obviously this force, it is acting in this direction. This is the gravitational force. And suppose displacement, it is in this direction, dr, in upward direction. So we have seen that du is equal to minus f dot dr. Okay, so here du, changing potential energy, it is minus F is the gravitational force dr cos 180 degree, because mg is acting in downward direction, dr is acting in the upward direction. Okay, so cos 180 is minus 1, so this becomes plus, so du is equal to mg dr. So if you integrate this, so this is 0 to h, if I am taking to height h, this is u initial, u final. So if you simplify this, what do you get? U final minus u initial is equal to mgh. Okay, now if I take the ground level potential energy as 0, so ui is equal to 0, so and uf is equal to u, so if I substitute this over here, what do I get? U is equal to mgh. So this is the expression for gravitational potential energy. Okay, see, everybody understands the expression that it is equal to mgh, but I was trying to stress that how to take the sign and all. Okay, this is by definition. This is by definition of potential energy. Okay, then force, we are calculating the work done by this gravitational force. Okay, it is a conservative force, and it is a conservative force. That is why we are using this condition. Okay, so this is the expression for gravitational potential energy. Similarly, we can get the expression for spring also. Okay, for spring we know that expression for potential energy is how much? Half kx square. Okay, use half kx square. Okay, now let us see two very fundamental concepts related to this spring. Okay, like suppose this is a horizontal rigid support and a spring is attached, and this is a mass attached to the lower end of the spring. The spring is in its natural length, this mass is attached, and I am holding this mass and I am gradually releasing. So this mass is coming down gradually, and because finally this mass stops at this particular position and there is some elongation. Okay, so this mass m is gradually lowered. Okay, and when the mass m is gradually lowered, you are asked to calculate the elongation in the spring. So when this mass is gradually lowered, the mass is in equilibrium. So if mg is the force in the downward direction, kx is the force in the upward direction. So mg is equal to kx. So x is equal to mg by k. So this is the elongation when this mass is slowly lowered. Okay. Second situation is, I am holding this mass. Spring is in natural length. This mass is attached to the spring. I am holding this mass, and mass is suddenly I am suddenly removing the hand. Now when I am suddenly removing the hand, this mass will fall down. Now when the mass falls down, there is elongation in the spring. Obviously, our common sense tells that the elongation will be more than this, because this mass is dropping suddenly. So when the mass is suddenly dropping, this mass is losing some potential energy. Suppose it is dropping through x. So the potential energy lost by this block, it will be how much? It will be mg into x. This is the potential energy lost by the block, this block, and it is equal to the kinetic energy. See, there will be elongation in the spring, so this is equal to the kinetic energy gained by the spring. So this is half kx square. Okay, so this is x cancel. So we have x is equal to 2mg by k. So this elongation, as you can see, it is 2 times the initial elongation when the mass was gradually released. Okay, so this is one very important concept. Okay, I hope this is clear to you. So this is the first part of the topic work energy power chapter. So I have divided the theory of the chapter in 2 parts. This is first part, then I will upload the second part. Okay, now based on this video, I am also going to give you some practice question. Okay, so you can try those questions and then give a feedback like whether you are able to solve those questions or not. In case of any difficulty, you can revert back. I will definitely help. Okay, so that's all for today's video. Okay, I hope this video is beneficial to you. My best wishes to you.